chapter 16. Okay, so we talked a lot about aromatic systems and understanding properties associated with aromaticity. In this next chapter, what we're going to really focus on, what we're really going to try to understand and explain is our goal is to understand sort of how do aromatic systems react? What are the patterns of reactivity? How can we explain these patterns of reactivity? And how can we utilize electrophilic aromatic substitution to generate compounds with defined substitution patterns? So if we want to make a target product, what is the best synthetic route using principles of aromatic reactivity? Okay. So electrophilic substitution reactions of benzene and their derivatives. So benzene is aromatic. It's a cyclic conjugated planar compound with 6 pi electrons, or more generally 4n plus 2 pi electrons. Benzene and other aromatic rings undergo electrophilic substitution reactions rather than addition. So we can install a variety of different unique functional groups via these aromatic substitution reactions. What we're going to talk about this chapter are the mechanisms for the electrophilic aromatic substitution reactions. We're going to talk about some important considerations when it comes to regioselectivity and directing effects. And then we'll start planning out some basic syntheses for aromatic systems. Okay, so let's just recall the basic mechanism for electrophilic addition. Now, this may seem like an odd starting point, but you'll notice many parallels between the electrophilic addition and substitution mechanisms. So in electrophilic addition, a nucleophilic pi bond is used to form 2 new sigma bonds. So in this case, our alkene is protonated by forming a carbon-hydrogen bond, breaking our pi bond, and then our carbocation is attacked by the nucleophile. Okay, so if we look at another electrophilic addition variant, such as the electrophilic addition of bromine as a Br plus equivalent, we end up with cyclization to give a bromonium ion, followed by addition of bromide from either face. Sorry. So we make our bromonium ion, that's this first step here. And then bromide then attacks from the opposite face at the most substituted carbon to yield the trans addition products. So these are the common addition mechanisms that you've seen from the previous organic course. Now, when we think about benzene, if we try to subject benzene to similar addition conditions, what we find is, one, benzene is not very reactive under typical addition conditions. It typically requires a catalyst. Further, benzene rings react via substitution rather than the rapid addition reaction common to compounds with a carbon-carbon double bond. So one thing that we clearly see is rather than observing the addition product, instead we observe substitution, where a hydrogen in our benzene ring has been replaced with a bromine atom. So we can conclude from this, from our previous discussions, that the carbon-carbon double bonds in benzene are substantially less reactive compared to a typical carbon-carbon bond. Now, what are some things that we can look at and discuss when we talk about this reaction? So first and foremost, the iron tribromide is added as a catalyst to polarize our bromine reagent. So in the presence of iron tribromide, we have our equivalent of bromine. We end up with coordination. And in turn, we end up with a functional equivalent of this iron tetrabromide anion and a Br plus equivalent. This is a very reactive electrophile. And as we've generated a pretty reactive electrophile, our benzene pi electrons are going to function as our nucleophile, and they're going to attack this Br plus equivalent. We in turn are going to generate our bromine adduct and a carbocation. Now, rather than an external nucleophile attacking our carbocation to give addition, instead, what we see is that our quote unquote basic components of our reaction mixture are sufficiently basic to remove this alpha proton, this proton adjacent to our carbocation, and promote elimination to regenerate our aromatic ring. That in turn gives us our substituted product and equivalent of HBr. So I'd just like you to note that this proton is very acidic, as elimination of this proton would generate a very, very stable aromatic system. So the main branching point when it comes to electrophilic aromatic substitution versus addition is once you get your carbocation, you see elimination to regenerate your double bond and regenerate your aromatic ring rather than addition into the carbocation. Does this mechanism make sense to everyone? So first, we need a very strong electrophile, and second, we see elimination of a proton to regenerate our aromatic ring rather than addition into our carbocation. Does this make sense to everyone so far? Any questions so far?
I have a question actually. I might have missed it as I was trying to draw this, but I saw that you circled the hydrogen and then you put very acidic.
Yep.
On there. Is that the hydrogen itself? Or?
Yep. This proton is a very acidic proton. It's very easy to remove because it's adjacent to a carbocation, and as a result, deprotonation and elimination of this proton is very facile.
Okay, got it. Thank you.
So that's why like bromide, which isn't typically thought of as a base at all, is sufficiently basic to pull off this proton and promote elimination. Does that make sense?
Yes, thank you.
Perfect. So let's refresh on the mechanism. So first and foremost, the aromatic ring pi electrons act as a nucleophile, attacking Br plus or whatever electrophile equivalent. E plus will be just our electrophile. And that gives a non-aromatic resonance stabilized allylic carbocation. Okay. One thing I do want us to note is carbocation can be delocalized via resonance throughout the ring. Next, H plus is eliminated in the presence of base to regenerate the aromatic ring. So we have attack onto our electrophile, then elimination to regenerate our aromatic ring. So this is the classic electrophilic aromatic substitution mechanism, and it's a nice two-step mechanism. Does this make sense to everyone? Any questions on this mechanism?
Yes, I have a question.
Yes, please go ahead.
What does it mean by a non-aromatic resonance?
Well, so if we look at this resulting carbocation, it's not aromatic, right? It doesn't have a fully, it's all of the atoms present in the ring are not conjugated. However, this carbocation is still allylic. And as a result, we can delocalize this carbocation across many atoms in our aromatic ring. Does that make sense?
Yeah, thank you.
So the cation is stabilized via resonance, but the overall ring system is not aromatic. We've broken aromaticity during the addition step. Does that make sense?
Yeah.
Perfect. So we've seen one example. Let's take a moment and let's think a little bit about what's occurring from an energetic perspective during the first step of electrophilic aromatic substitution. So if we compare electrophilic aromatic substitution to the first step of electrophilic addition, if we compare an alkene to an aromatic benzene ring, there are two main features of this graph that I'd like to draw your attention to. So first and foremost, if we look at the net change in energy for these two reactions, if we look at the net change in energy for these two reactions for this first step, is this first step exergonic or endergonic? Is this first step exergonic or endergonic? Is that intermediate that we're generating higher or lower in energy than our starting material?
Higher.
It's higher in energy. So what would we call that if we have a net increase?
Endergonic.
Yep. So this would be an endergonic step. So in both cases, this first step is endergonic. And as a result, if we think about each of our transition states for an endergonic reaction, our transition state will resemble the species closest in energy to that transition state. And in turn, for an endergonic reaction, the transition state will resemble our products. So our transition states will resemble these intermediate carbocations. So factors that stabilize our carbocation will also stabilize our resulting transition state. Okay, what's another thing that we notice for these two reactions? So if we think about our activation energy, and if we think about the activation energy for this reaction, and we compare the activation energy for a benzene ring undergoing substitution to an alkene undergoing addition, what do we notice for electrophilic aromatic substitution? Is the activation energy larger or smaller in general?
Wait, for which one?
So for the electrophilic aromatic substitution, so this curve in black describes the reaction coordinate energy diagram for electrophilic aromatic substitution. So this first step is showing what would happen if you have a reaction of a benzene ring. And as the chat's pointing out, this activation energy is larger for electrophilic aromatic substitution in general. Okay, so it takes a pretty large amount of initial activation energy for this first rate determining step. And the reason for that can be explained because in this first step, if we start out with our benzene ring and we are attacking and forming a bond to our electrophile, we are breaking aromaticity, and that in turn leads to a higher energy intermediate, right? This carbocation is a pretty high energy intermediate compared to our starting material. Okay, so we've looked at a few things related to the reaction coordinate for electrophilic aromatic substitution. Now let's talk a little bit about, let's sort of refresh these features. So first, we have a larger activation energy as the substitution step generates a non-aromatic cationic intermediate, which is higher in energy than the starting aromatic system. Now, one consequence of this, and one sort of way that we go about coaxing this reaction to occur and minimizing this required activation energy is by using a stronger electrophile. So generally, strong electrophiles are required for aromatic substitution reactions to help, and you may even have to resort to higher temperatures as well. And these strong electrophiles are necessary because they help reduce this activation barrier and reduce the activation energy required for this reaction to occur. So any questions on this idea? So we looked at our energy diagrams. We concluded that the activation energy for electrophilic aromatic substitution is generally quite large. And as a result, we generally have to use strong electrophiles or high temperatures to force this reaction to initiate. There is a question in the chat. How would you go about making the addition product? So to answer that question, generally the addition product is never observed for aromatic systems. The benzene ring is and the substitution product is so much more stable that under the reaction conditions, you will see reversible reaction and equilibration, and ultimately the products will funnel towards the substitution product. Because even if you did get addition, that addition product could in turn undergo elimination and you'd go back to your substitution product. We'll see a diagram about that in a moment, but generally you don't see the addition product. Does that answer your question? Perfect. So with that, let's look at this diagram and try to answer the question, why do we see substitution over addition? So we have this first step, it has the highest activation energy. So we know that step number 1 is going to be rate limiting. Step 2 is not rate limiting, and we have two choices. We can either funnel to substitution or addition. Now, one thing that I'd like you to note is that if we think about this activation energy for the reverse reaction, so if we're going from the substitution product back to this intermediate, looking at this activation energy for this reverse reaction, it's pretty large, right? Does everyone see this huge difference in energy between our transition state and the substitution product energy? Does everyone see how if we wanted the substitution product to go back to this intermediate, we'd have to surmount a very large activation energy? Comparatively, for addition, the activation energy for this reverse reaction is small. So then, we can think of this addition as being reversible. Even if addition does occur, we can revert back to this carbocation intermediate or eventually funnel into our substitution product. Because our substitution product is so much more stable than the addition product, under the reaction conditions, and because the addition step is relatively reversible, we will see almost none of the addition product and almost 100% substitution product. Does that make sense to everyone? Essentially, it's this idea that the addition product is so much higher in energy, and this step, the activation barrier, can be surmounted under the reaction conditions. This step is reversible under the reaction conditions for addition, that we can funnel to the substitution product. And then once we have our substitution product, it's very difficult to surmount this activation barrier and go back to this cation intermediate. Does that logic make sense to everyone? Does that explanation make sense? So essentially, as both steps are reversible, the substitution product is favored under the reaction conditions. Okay, so let's keep going now, and let's look at other aromatic substitutions. We can just as easily incorporate other halogens such as chlorine or iodine. Not fluorine, fluorine's too reactive, but for chlorine, in the presence of iron trichloride or iron 3 chloride as our catalyst, we can get chlorination of our aromatic rings. Iodine, to activate iodine, we treat it with a copper salt to make an iodine plus equivalent. We need a stronger electrophile. This is a general theme for aromatic substitution. The mechanism is identical. We attack our electrophile and then we eliminate a proton to regenerate our aromatic ring. Any questions on variants involving chlorine and iodine? We can even draw the mechanism for chlorine just to show everyone what's going on. it's identical to the bromination mechanism. Any questions on chlorine and iodine variants?
Professor, one quick question.
Yes.
On the reaction on the first arrow, where's the arrow coming from on the aromatic one to Cl?
So it's coming from the pi bond. So our pi bond in our aromatic system is our nucleophile, and we use our pi bond to form a carbon chlorine bond. Does that make sense?
Yeah, and then so on the second arrow, it's from the bond two, right? To the iron.
Yes. So it's essentially this idea that the iron 3 chloride activates our chlorine by coordination.
Oh, okay.
And essentially what I'm trying to show is we're functionally generating an equivalent of Cl+, but we don't have like formal Cl+ floating around in solution. It's more like we've activated this chlorine by coordination of our Lewis acid. Does that make sense?
Yeah, thank you.
Mm-hmm. Any other questions on this? Okay, so let's look at another variant, this time with another electrophile. In this case, we're looking at aromatic nitration, so introduction of a nitro group, NO2. So in this case, we're going to need a pretty strong electrophile, an electrophilic equivalent of NO2. And in this case, combination of nitric acid and sulfuric acid produces NO2+, or the nitronium ion, which is a pretty strong electrophile. So this is an activated enough electrophile for electrophilic aromatic substitution. Once we've generated a trace amount of this electrophile, the aromatic ring then reacts with the electrophilic NO2+, and we generate our resulting NO2 adduct. So in this case, if we took benzene and we subjected it to nitration, we generate nitrobenzene. So to talk about this first step where we're generating our electrophile, nitric acid is first protonated. So in this case, we protonate. Let me draw out sulfuric acid a little bit. So we protonate one of our oxygen atoms, and then from there, we eliminate an equivalent of water, and that generates our nitronium ion. Notice these two steps are equilibrium steps, and they are reversible. However, any amount of nitronium ion that we generate will react very quickly. So in turn, we start to funnel this equilibrium to produce a little bit more nitronium ion, which then reacts. So by Le Chatelier's principle, we're always generating a little bit of this reactive electrophile that is then immediately consumed under the reaction conditions. So how does this nitronium ion react? So as always, our aromatic ring, our pi electrons serve as our nucleophile. They attack our electrophilic nitronium ion. We generate our carbocation, and then we eliminate a proton in order to regenerate our aromatic ring. So in this case, the most reasonable base under these conditions would be water. Does this mechanism make sense to everyone? Does this mechanism for nitration look pretty familiar to everyone? It's almost identical to bromination, chlorination, etc. The only thing that's different in all of these mechanisms is how the electrophile is generated. Now, why is this important? Well, the nitro group is a really useful handle that can be reduced to an amine functionality. It's pretty hard to get an electrophilic source of nitrogen that has the same oxidation state as an amine. So typically a nitro group is an easy way to install the requisite nitrogen functionality, and then you can convert this nitro group into the amine. So these are useful, almost synthetic equivalents or sort of functional group handles that can be interconverted with pretty simple reaction conditions. So it's very rare to directly install the amine, but it's pretty easy to directly install like a nitro group and then reduce it. Does that idea make sense to everyone?
And why would you want to reduce it?
Well, if your desired product contains an amine, it's easier to install that amine in the form of a nitro group. Further, if your target, if the target that you're trying to synthesize, and if you're starting from a starting material that lacks the amine functionality and you go through a nitro group, you can get an amine functionality from your nitro group. So it depends on what you're trying to synthesize, but this is a useful conversion to know, as it's pretty common to install a nitrogen via aromatic nitration and then reduce it off. Does that answer your question?
Yes, it does. Thank you.
Perfect. So another variant, another electrophilic aromatic substitution reaction that's pretty common is aromatic sulfonation. So in aromatic sulfonation, we have substitution of hydrogen by HSO3. So in this case, our reactive electrophile is going to be generated from sulfuric acid reacting with SO3 to yield the electrophile HSO3+, shown here. Once we've generated our electrophile, the aromatic ring then reacts with the electrophilic HSO3+. So in this case, once we've generated our HSO3+, just like before, our aromatic ring attacks our electrophile. And then once we've generated our carbocation, an equivalent of base is going to pull off our proton, and we're going to regenerate our aromatic ring. So this is a great way of generating sulfonic acids and installing a sulfonic acid group onto our aromatic ring. To answer the question on the chat, the amine group couldn't act as an electrophile. Amines, sort of by their very nature, are nucleophilic. If you want to get them to act as an electrophile, you have to adjust the electronics of your system. So you like something like this, for example. But those kinds of nitrogen electrophiles aren't typically reactive enough for direct aromatic substitution. It's easier to go through the nitrinium ion in many cases. With that aside, does anyone have any questions on aromatic sulfonation? So in this case, our electrophile is HSO3+. Once we've made our electrophile, we have the same general electrophilic aromatic substitution mechanism. So not much has changed in terms of the mechanism. We have attack onto our electrophile, elimination to regenerate our aromatic system. Any questions that I can address based on this? Any questions that I can address for this mechanism?
No.
Okay, so then let's keep going then. And now this is a reaction that requires a little bit more care and attention. So for aromatic alkylation, we have what's known as the Friedel-Crafts reaction. It's a very useful reaction. And you'll see variants of the Friedel-Crafts reaction employed when you're dealing with carbon-carbon bond formation from carbons involved in aromatic rings. So let's talk about this basic mechanism, and then we'll talk about some variants of it. So first, in order to generate a reactive carbon electrophile, a Lewis acid is required to activate an alkyl chloride or any other alkyl halide besides fluoride. The resulting activated alkyl chloride will in turn react and generate a carbocation. This is going to be our reactive electrophile for the Friedel-Crafts alkylation. This resulting carbocation will react with the aromatic ring via electrophilic substitution. So just like before, we've generated our electrophile, we attack our electrophile with our aromatic ring, we have formed a carbon-carbon bond, and then in turn, we regenerate the aromatic ring by eliminating a proton. So in effect, we have replaced a proton with an alkyl group. Now, this is a pretty powerful reaction. It's another really landmark reaction to form carbon-carbon bonds. Those are very useful reactions. Those carbon-carbon bonds are sort of the centerpiece of the skeleton of many molecules. However, the Friedel-Crafts reaction does have some limitations. And before we talk about those limitations, does this mechanism make sense? We're attacking a carbocation and then eliminating a proton to regenerate our aromatic ring. Does that make sense to everyone? Okay, perfect. So here are some issues. Here are some issues with the Friedel-Crafts reaction. So in many cases, polyalkylation occurs. So poly meaning many. So we often see installation of multiple alkyl group equivalents. This is because the installed alkyl group actually activates the ring to further reaction. So we know that alkyl groups on the ring are ortho-para-directors. And in turn, what we see is that the second alkyl substituent generally will add para to the first. So as you notice, the major product for this Friedel-Crafts reaction is the polyalkylated product, and we have a 1,4 relationship or a para relationship between our two substituents. So this is one common issue with the Friedel-Crafts reaction for alkylation. It doesn't stop at the first alkylation in many cases, which could be useful or not very useful, depending on the system you're trying to make. Does this make sense to everyone so far?
Professor, could you go over ortho-para directors? What does that mean?
So we're going to talk about this idea a little bit later on, but essentially this idea is when you have an alkyl group, such as an R group, that in turn activates the ortho and para positions for reaction and for substitution. Just to give you a little preview, the reason why this alkyl group is an ortho-para activator is that when we see reaction and when we install our second alkyl group that I'll call R, this carbocation, when it's adjacent to this alkyl group, is stabilized. So that's what we mean by ortho-para directors. Essentially, different functionalities on your aromatic ring can stabilize carbocations at different spots on the aromatic ring, and in turn promote reaction at ortho, para, or meta positions, depending on the functional group's electronic character. Does that answer your question?
Yeah, thank you.
We're going to be talking more about ortho-para directors in a moment, but this is important context to help us understand, and it's important to note to help us understand why we specifically see this para product when we observe polyalkylation. I have a student asking for polyalkylation, if we have straight chain alkanes. To answer that question, we have to address the second limitation of the Friedel-Crafts reaction. So these may seem like relatively straightforward limitations at first glance, but it's important to think about why these limitations exist. So first, the alkyl halide halogen must be bonded to an sp3 hybridized carbon. So only alkyl halides are useful. Aryl halides and vinylic halides are not reactive because the carbocations are too high energy to form. So a lot of the principle behind what makes a viable electrophile, or carbocation to react via Friedel-Crafts alkylation is based on this idea of carbocation stability, right? We're never going to get a vinyl carbocation easily, for that matter. The second limitation that we have is that because we are dealing with a Lewis acid, and because we are dealing with sort of relatively strong carbon electrophile, rings containing basic amino groups that can react with Lewis acids or rings that contain strongly electron withdrawing groups like carbonyls do not react because both will deactivate the ring. So there are two cases to look at. The first of which is the case where we have an amine. So if we have an amine, this amine has a Lewis basic lone pair, right? This lone pair is a Lewis base. It's also a nucleophile. So if we have any Lewis acid floating around, we are going to coordinate our Lewis acid. And this in turn deactivates our ring. Now, when we talk about these electron withdrawing groups, so these electron withdrawing groups deactivate the ring. If we think about what happens if we have an electron withdrawing group, like a nitro group, for example, this nitro group is electron withdrawing, and in turn, our ring is less electron rich, and our pi bonds are less nucleophilic. So as a result, if we try to subject any aromatic ring with a strong electron withdrawing groups to a Friedel-Crafts reaction, what we will instead see is no observed reaction. The ring is not electron rich enough, and the ring is not activated enough for the Friedel-Crafts alkylation to occur. So the key thing you need to know from this limitation, we have to make sure that the ring is free of amine functionalities that are unprotected, because those amines can react with our Lewis acid or react with our electrophile, and that deactivates the ring. And electron withdrawing groups deactivate the ring and make it so that it's not sufficiently nucleophilic for Friedel-Crafts alkylation to occur. Do these limitations make sense? To answer the question in the chat regarding the first limitation, so this would be an example of a vinyl halide where our halogen is directly attached to the sp2 carbon in our double bond. Well, this would be an example of an aryl halide where our halogen is directly attached to our aromatic ring sp2 carbon. And the reason why aryl and vinyl halides aren't reactive as Friedel-Crafts electrophiles is because generating this aryl carbocation or vinyl carbocation, these carbocations are very high in energy, and as a result, they're very difficult to form. So you're not almost never, you're never going to see Friedel-Crafts reaction of vinyl or aryl halides because there's such a huge energetic barrier to generating this aryl or vinyl carbocation. Did that answer your question? Did that address your question? Well, the Friedel-Crafts alkylation by definition will only install alkyl groups. So this polyalkylation issue only occurs in the Friedel-Crafts alkylation. It's not based on the electrophile strength. It's more based on the fact that these alkyl groups activate the ring to further reaction. So each time you add your alkyl group, the substrate gets more and more reactive towards substitution. And that's why polyalkylation is such an issue for Friedel-Crafts alkylation reactions. Does that make sense? Okay, so the three major limitations. First, we get polyalkylation. That's a problem. Vinyl and aryl halides aren't reactive enough electrophiles. You're not going to make an aryl or vinyl carbocation. And the third limitation is the aromatic ring cannot have an electron withdrawing group. It cannot be deactivated. If the ring is deactivated, then it's not nucleophilic enough, and the carbocation generated from addition is not stabilized enough, and as a result, the activation barrier is too high. Okay, so electron withdrawing groups and Lewis basic amine functionalities are not compatible with these reaction conditions. Okay, any questions on these limitations? Any questions on these limitations?
No.
Okay, so let's look at this next case and let's look at the next major issue for Friedel-Crafts alkylation. And this will answer the student question, what about primary substituents? Well, primary substituents have a host of issues. Because we're going through a carbocation intermediate, the Friedel-Crafts alkylation is notorious for carbocation rearrangements. So rearrangement of our carbocation electrophile can occur, yielding a mixture of products. These rearrangements via hydride or alkyl shifts will occur to generate the most stable carbocation. So for example, in this case, if we have chlorobutane, we generate our resulting carbocation. This is a primary carbocation. We would much rather have a secondary carbocation. So to generate the more stable secondary carbocation, a hydride shift occurs. Does this idea of a hydride shift look familiar to everyone? We saw this in earlier discussions of carbocation stability and carbocation rearrangements in organic 1. So essentially a carbon-hydrogen bond shifts over, an equivalent of H- or hydride shifts over, and we generate a new, more stable carbocation. So this is why often for the Friedel-Crafts reaction, you don't see primary alkyl chlorides or alkyl halides used because they're so prone to rearrangement. And as we see, the major product actually occurs from the secondary carbocation intermediate. Does that answer your question? Or does that help provide context to your question? Perfect. Now, this can get really, really frustrating if you're trying to get a defined product to form, because if you have a primary carbocation next to a highly substituted T-butyl group in this case, or an isopropyl group, The moment you generate your primary carbocation, you're just one alkyl shift away from a highly activated and a much more stable tertiary carbocation. So as we know, which of these carbocations is more stable? Which of these carbocations is lower in energy? The primary or the tertiary carbocation? The tertiary, right? It's stabilized by an increasing number of hyperconjugation interactions, and generally increasing substitution on your carbocation results in a more stable carbocation. Okay, so as we can see, alkyl and hydride shifts are a big problem, and they limit what kinds of products we can reasonably get out from the Friedel-Crafts alkylation reaction. Does that idea make sense to everyone? Okay, so let's keep going now. And let's take a look at an alternative to Friedel-Crafts alkylation, the Friedel-Crafts acylation of aromatic rings. This is a preferred alternative to Friedel-Crafts alkylation if you want to mitigate some of the reactivity and selectivity issues encountered during the Friedel-Crafts reaction. So in this case, we have a reaction of an acid chloride or acyl chloride and an aromatic ring in the presence of a Lewis acid, such as aluminum trichloride, introduces the acyl group. The Lewis acid activates the acyl chloride to generate an acylium ion, which looks something like this. The acylium ion then reacts with the aromatic ring via electrophilic substitution. So in effect, we have replaced a proton with our acyl group. So in terms of the mechanism, first, the Lewis acid activates the acyl chloride to generate an acylium ion. Once we have our acylium ion in place, the acylium ion is a pretty reactive electrophile. It reacts with our aromatic ring via electrophilic substitution. And then finally, we regenerate our aromatic ring via elimination. So, any questions on this mechanism? Any questions on this mechanism? Okay, so one benefit of acylation is that acylation is more controlled as the acyl group deactivates the ring for further reaction, right? If we have an electron withdrawing group in general, so if we have an electron withdrawing group and we try to run Friedel-Crafts acylation conditions, as we talked about for alkylation, will we see a reaction if we have a deactivated ring? If we have a deactivated ring, will we see a reaction? No, right? And this is a benefit because what that means is if we subject an aromatic ring to Friedel-Crafts acylation condition, we will get one and only one installed acyl group. If we try the same trick with alkylation, we will get potentially quite a mess. So, acylation gives you a little more control over reactivity. Does that idea make sense to everyone? Does that first benefit make sense? Okay, perfect. Now, there are a few other benefits for the Friedel-Crafts acylation. One, the acyl cation doesn't rearrange. So if we try to run alkylation using this primary alkyl chloride, we're primarily going to get reaction at the secondary position, and we also see polyalkylation. So these are the two hallmark issues with Friedel-Crafts alkylation. With acylation, you can add the straight chain acyl or acyl group to the ring, and then we can reduce the carbonyl without rearrangement. So the carbonyl of the acyl group can be reduced after substitution under relatively facile conditions. So in this case, we see reaction with the desired regiochemistry. We get reaction at the primary position, quote unquote, and we only see monoalkylation. So Friedel-Crafts acylation and alkylation are two complementary techniques, and depending on the regio control and control over reactivity that you need, you may want to resort to Friedel-Crafts alkylation, which works fine for certain substrates, or acylation if you want a little bit more control over selectivity. Does that idea make sense to everyone? So again, oh, this one right here, because it comes from the secondary carbocation, right? So essentially what I'm trying to convey here is that if you react this primary alkyl chloride, it'll rearrange, you'll get a secondary carbocation, and that secondary carbocation is what's reacting. Comparatively, if you use an acyl chloride, you go through this acyllinium ion, and this acyllinium ion doesn't rearrange. So you get reaction at the design, and you get to form the desired carbon-carbon bond, and then you can simply reduce off this carbonyl functionality with this zinc-mercury amalgam in the presence of acid and heat. So in effect, Friedel-Crafts acylation serves as another means of installing alkyl groups, and it installs alkyl groups that the Friedel-Crafts alkylation struggles to install with regio and chemoselectivity. Does that answer your question? Does this idea make sense to everyone? So the other benefit is that when we have an acyl group versus an alkyl group, the acyl group has a different directing profile compared to an alkyl group. So if you try to brominate this following group, when you have an acyl group in place, this acyl group is a meta-directing group. So what that means is it directs substitution reactions to install their functional group, install the electrophile at the meta position. If we try this same reaction with an alkyl group in place, we will see reaction primarily at the ortho and para positions. So as we notice, the acyl group promotes substitution at the meta position, while your alkyl group promotes substitution at the ortho and para position. So Friedel-Crafts acylation and alkylation also install two different types of directing groups. And depending on what product you're aiming for, you may need to sequence acylation or alkylation. Now, this is really useful because it allows you, in effect, to generate these very difficult to get functional group patterns. And it allows you to install an alkyl group, but retain a meta-directing group throughout your synthesis. We'll talk more on directing groups in a moment, but this is just a critical piece of utility associated with the Friedel-Crafts acylation. Acyl groups direct reaction to different positions. Does everyone see the difference between the acyl and alkyl group? Okay, so here is a summary of electrophilic aromatic substitution, the common Lewis and Bronsted acids used, the name of the reaction, and what electrophile is installed. To make sure we're familiar with these mechanisms, what we're going to do is we're going to practice drawing some mechanisms. So I'll do the first one, and then the class will be responsible for these next few problems. So in this case, we're asked to draw a mechanism for the following reaction and predict the products. Okay, so first things first, we have our source of Cl plus equivalent. So we're going to attack our electrophilic chlorine equivalent. We are going to generate our chlorine adduct, and then we're going to eliminate our proton to regenerate our aromatic ring. So we've in effect replaced this proton with a chlorine atom. So this would be the mechanism, and this would be the predicted product for the electrophilic chlorination of benzene. Any questions on this mechanism?
Professor,
Yes.
is the bond from the H going, the arrow going to the carbocation?
It's going to form a double bond. So it's going, you're eliminating this proton and you're forming a double bond between these two carbons. And that's what regenerates our aromatic system.
Okay, thank you.
Any other questions that I can address? Okay, so let's try the following example, and I'd like students to try to use the annotate tool or to share screenshots of their proposed mechanism in the chat, or share their input for the mechanism steps verbally or in the chat. And let's try to draw a mechanism for the following reaction and predict the products. So let's take about 4 to 5 minutes to work through this example, and then we'll discuss. And remember, you can use the annotate function under the Zoom meeting options. So if possible, I'd like to see some students try to annotate the proposed mechanism or share their ideas for the proposed product in the chat, verbally, or on the class whiteboard. Okay, so we see a student has drawn activation of our acyl chloride. And what intermediate would we generate from our acyl chloride? What is the electrophile for this Friedel-Crafts acylation reaction? So we generate the acylium ion, though it technically should be drawn with a triple bond as we kick this lone pair down like so. But the idea is correct. Would you be able to continue the arrow pushing mechanism? So you form this carbon-carbon bond, and what happens next? What bonds do we break? Does the class have a suggestion or input on this mechanism? So after attack onto our electrophilic acylium ion or acylium ion, we form our desired carbon-carbon bond. And then to regenerate our aromatic system, what happens next? And I think this is missing a carbon. There we go. But to regenerate our aromatic system and to regenerate our aromatic ring, what happens next? Does anyone have a suggestion in the chat? Or would anyone like to draw out the last step? What do we think? So our base equivalent is going to remove our proton, and that proton is going to eliminate, and we'll regenerate our aromatic ring. Perfect. Yep, this mechanism looks reasonable to me. So let me clear this and then we'll discuss, and I'll redraw this just for our reference. So in the first step, we generate our acylium ion. So our aluminum trichloride coordinates, we eliminate chloride. 2, 3, 4, 1, 2, 3, 4. We generate our acylium ion. The acylium ion then reacts with our aromatic ring. We generate our carbocation, and in turn, our base is going to pull off a proton, promote elimination, and in turn regenerate our aromatic ring. Does this make sense to everyone? Does this mechanism make sense? Any questions on this mechanism? The pi bond in the ring is our nucleophile. Our acylium ion is the electrophile. So this is just a resonance stabilized form of this. So the acylium ion is a resonance form of the cation that you get if your chloride leaves. And that resonance form is more stable. Did that answer your question? And you need all of the steps for this to be a complete mechanism. Well, it is a major resonance contributor because the acylium ion both follows the octet rule and it attempts to stabilize this relatively unstable sp2 cation. So generally, if you have a carbocation adjacent to an atom with a lone pair, then you can stabilize your carbocation via resonance. And even though oxygen is electronegative, by stabilizing this carbocation with electron donation, the donation of electron density from an adjacent atom with a lone pair will inherently stabilize your carbocation and reduce its electron deficient character. So when you're drawing out the actual reactive species, yes, it's an acylium ion. It would be more correct to draw the acylium ion rather than the carbocation, even though they're both resonance forms of each other. They're identical species. It's just more commonplace to draw the acylium ion. Does that answer your question? Perfect. Okay, so let's keep going now and let's try to draw a mechanism for this following reaction. And I'd like students to share their proposed mechanism on the class whiteboard, or you can also share a screenshot in the chat, or you can voice your proposed steps in the mechanism in the chat or verbally, and I'd be happy to provide feedback. So let's work on the following mechanism for 4 to 5 minutes, and then we'll discuss. And again, don't be shy to share your proposed mechanism in the chat or verbally. And I'd like to see a few annotated mechanisms shared for this electrophilic aromatic substitution mechanism. Would anyone like to try using the annotate tool to share their mechanism for this reaction? And remember, there's plenty of space on this class whiteboard, so multiple people can annotate. I would highly recommend practicing putting pen to paper for drawing these mechanisms because it can help reveal questions that you have or potential parts of the mechanism that you're unsure about. And there's no better time than when the instructor is here to provide feedback. You can also share pictures of your drawn mechanisms in the chat as a screenshot, as long as it's a compatible file.
Professor, I have a question.
Yes, please go ahead.
Isn't the first step is the HNO3 H2SO4 reacting to one another?
Yes, that is correct. So the first step we have to complete for this mechanism is generating our reactive electrophile. So we may want to draw out nitric acid in full so we can show the arrow pushing step to generate our electrophile, which is going to be the nitrinium ion, which is NO2+. So let's show that first step, and I see multiple people annotating. That's perfectly okay. There's plenty of space on the class whiteboard for that. And nitric acid HNO3 looks like this, just for everyone's reference. So we have nitric acid, we treat it with sulfuric acid, and what is that sulfuric acid going to do? And you may want to draw out sulfuric acid in full. Let me take a look. A student has shared their mechanism. Will you be able to the files in the chat, it'd be best if they're a PDF or a JPEG, since when you send it via Zoom, some files don't open properly. But I'd be happy to provide feedback on any files submitted. So looking at the proposed mechanism, we have a student drawing out that you protonate nitric acid with sulfuric acid. That's correct. We're activating this alcohol, we're activating this leaving group. So rather than kicking out hydroxide, we're kicking out water. And this sets up our nitric acid to eliminate water and make our reactive nitrinium ion. Yep. So this looks perfectly reasonable. Now let's show that elimination step. And don't worry, there's plenty of space in the class whiteboard, so don't be shy to share your proposed mechanisms. And of course, you can also share your screenshot of your proposed mechanism in the chat as a PDF or JPEG image. So we have a bunch of students at the first step where you've protonated nitric acid. And how do we get the nitrinium ion from there? Once we protonate nitric acid, what do we get from there? Yep, we eliminate water. Yep. Okay. Okay, and now that we have the nitrinium ion, now that we have our nitrinium ion, what can we do with it? And we have some space at the bottom, and you may want to take the full bottom you may want to take the full row at the bottom so you can draw each step. And some students are sending their proposed mechanisms in the chat. Let me take a look. If possible, a PNG file is best. And for the step that I saw sent in the chat just a moment ago, for the protonation step, just draw the oxygen lone pair pulling off a proton, just like we see in yellow. Let me take a look. Yep, and I see a lot of students showing the exact same step. Once we get our nitrinium ion, the aromatic ring attacks the nitrinium ion. The only thing to keep in mind is that when you attack your nitrinium ion, your product will be a carbocation. So I have students that are skipping a step. So once we get the carbocation, after we form our bond to nitrinium ion, how do we regenerate our aromatic ring? So I see many mechanisms in the chat and the mechanism in yellow. So in order to regenerate our carbocation, make sure to draw out the carbocation that you make and then show that elimination step. Does that make sense to everyone? So we see one of the students who's annotating in purple has drawn out the carbocation, and now all they have to do is show the elimination step where you eliminate a proton. So in yellow, they drew the correct addition mechanism, but the product itself would be this carbocation. And all they have to do is show elimination to regenerate our aromatic ring. So let's keep working through this. There's plenty of space on the class whiteboard, and I'm just looking to see and to find, once a student has completed this mechanism perfectly from start to finish, then we'll talk about it. Okay. So let's take a look and let's pay attention to this mechanism in red. The contributions from all of this class, both verbally in the chat with pictures and on the class whiteboard, has been really helpful so far. So let's talk about this first step. So the first step, we protonate nitric acid, we eliminate water, we make the nitrinium ion. Everyone's gotten that perfectly correct. The next step, our aromatic ring attacks and we generate this carbocation. Now, in order to regenerate our aromatic ring, rather than a proton just eliminating on its own, we have an equivalent of base, in this case water, pull off our proton. So to rewrite this so that way everyone can see the steps for this mechanism, it's great to see so many people annotating, and I find also, I noticed for many students as they annotate and draw pictures for this mechanism, that you begin to notice sort of aspects of the mechanism that you'd like a little more clarification on, or steps where the arrow pushing may not be fully clear just yet. And that's part of why I encourage everyone to try putting pen to paper for these mechanisms. So for the first step, we're going to protonate our alcohol. This is an equilibrium, so I'll draw it as such. Oh, whoops, that's resonance. So let's draw equilibrium arrow. There we go. That generates our protonated nitric acid. We're then going to eliminate an equivalent of water. That's going to generate our nitrinium ion. Now that we have our reactive electrophile in place, we are going to attack our electrophile with our nucleophilic pi bond. And we're going to form our carbon-nitrogen bond. Then what we're going to do, well, we get water from the elimination step. Yeah, there's also water naturally present in any sulfuric. The sulfuric acid is typically aqueous, as is nitric acid. Neat nitric acid and sulfuric acid are gases, so it's always going to be run in a little bit of water. But there are plenty of other competent bases present in the solution. You can even draw like HSO3 minus as a competent base. It's not a strong base, but it's strong enough to pull off our proton and promote elimination. Okay, so now that we have our carbocation, water is going to pull off our proton. And in turn, we're going to regenerate our aromatic ring. So we end up with our nitration product. Does this mechanism make sense to everyone? Does this example make sense? So I really encourage you to practice drawing out all of the mechanisms that we've gone over today. We'll do a few more examples where we draw some mechanisms next class session. And then what we'll do is we'll practice and we'll start to talk a little bit about directing groups and we'll start to understand why the reactions are selective for certain positions. Why do we see selectivity for the ortho, meta, and para positions when we have different substituents? But you have to understand these basic mechanisms before we can start to understand how directing groups function. So, any questions before we close out the lecture portion for today? Okay, so what we're going to do is we will take a quick break.